All right, class, this is ionization energy and electron affinity. So, ionization energy, the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. That means the outermost electron. So okay, we'll get into it. First ionization energy is the energy required to remove the first electron outside. Not the one closest to the nucleus, but the one most further outside. Second ionization energy would be the next further outside one moved, and so on. So typically we only worry about the first ionization energy because that tells us a lot, but sometimes we get into the second and third, and I'll explain why we would do that. So let's move on here. It's requiring more energy to remove each successive electron. So first of all, and I'm kind of confused that they don't actually show. Okay. All right, so let me show you this. For ionization energy, if we're talking about something like sodium, it would look like this. We would have first our gaseous, and then it would be Na, still gas, with a +1 plus 1 electron. Okay, E with a minus. So that is our that's our formula, or how we represent ionization energy. So it requires more energy to remove electrons. If I want to take, this is for the first ionization energy. If I want to take a second ionization energy, it would look like this then. It would still be Na with a plus like that, and then I would go Na with a +2 plus 1 electron. So that's what the second ionization energy of sodium would look like. Now clearly you can see that it takes 495 kilojoules per mole to remove that 1 electron, and then the second one, take a look at that, 4,562. That's quite a jump. That's almost a 10-fold jump. It's actually a 9-fold jump in the amount of energy it takes to remove the second electron from sodium rather than the first. Now why is that? When all valence electrons have been removed, the ionization energy takes a quantum leap. That means it takes a large step. That's what's in the blue. So if we go from a valence electron of 495 to an inner core electron, it goes 4,562. So clearly there's a huge jump there, and that happens for all of them. Notice that sodium's in the first group, so it has 1 valence electron. Magnesium's in the second group, so it has 2 valence electrons. Notice that it doubles here pretty much, but then a massive jump when it goes for the first core electron. These electrons in the blue here that are being removed, they are all core electrons, which means they have the electron configuration of noble gases. That's why. I didn't mean to write that all one word, but noble gas configuration, and that's why there's so much more energy to pull off a noble gas configuration. Okay, so let's keep moving. Take a look at the trends of the first ionization energy. Obviously, we start in the upper right-hand corner of the periodic table. That is the highest electron ionization energy, and it decreases as you go down a group, and it decreases as you go from right to left. In other words, increases as you go to the right, but decreases as you go down. All right, so these trends we're going to want to know. Like, here's the easiest way to do it, in my opinion. Whoa, I don't know what's going on with the thing there, but when we're talking about the highest amount, the highest electronegativity, why do I keep saying that? The highest ionization energy, remember what that is. That's helium, and that will tell you what the rest of the pattern is. Okay, so the highest ionization energy is helium. That means that if you go across from left to right, it increases, and if you go down, it decreases, because that's where helium is in the periodic table. Okay, so trends in the first ionization energy. Take a look at this again. Look how it goes from hydrogen, this one's right here is hydrogen, and then it goes up to helium. And then it drops all the way down to lithium here, and then it goes back up for beryllium and drops down just a little bit for boron, and then goes up, drops down just a little bit, and then goes up and goes up. Okay, so you start to see this trend where it starts, the pattern starts to repeat every time they get to a new period, which is why the periodic table is set up that way. So trends in the first ionization energy, however, there are two apparent discontinuities in this trend, and it happens here and it happens here for both of them. Now, why is that? Well, the first group occurs between groups 1a and 2a. The electron removed in the p orbital rather than the s orbital. So here we remove from the p orbital there as opposed to the s orbital there. And that happens. That's why it doesn't follow a clear pattern. Electrons further from the nucleus for the p orbital, and a small amount of repulsion by the s electrons. So that accounts for the differences. You don't need to memorize that. The second one occurs between 5a and 6a. Electrons removed comes from doubly occupied orbitals. So that accounts for this right here. That means that we're going from a doubly occupied orbital, looks like this. Those are single occupied orbitals. The next one then, this would be like the 2p, and this would be for nitrogen, but then oxygen would have the 2p. For the first time, we got 1, 2, 3, and then the fourth one goes like that, and that's the doubly occupied orbital. That's what that is. So that's the reason for the second issue. Energy change accompanying addition of the electron. So what happens here is when we add an electron, this is like the opposite. Okay, this is the opposite of ionization energy. So we're now checking the energy change for when we add an electron on. Notice that this is something that chlorine wants to do because now on this side here, it has a noble gas configuration. Okay, so that's a good thing for it. Let's take a look at some numbers. So chlorine, notice that it has a higher negative, which means it likes that, likes that, likes that, and likes that. And then when you get over here, these don't like that, don't like that. That one can go either way, doesn't like that, definitely doesn't like that. Okay, so in general, electron affinity becomes more exothermic or more negative as you go from left to right across the row. That is the basic, although it doesn't always follow that. Notice there's a drop between these two, a drop between these two, and you would think you'd see it continue to go up. So it doesn't always hold true. So electron affinity, again, there are, however, discontinuities in this trend, and I just showed them to you. So this says the first occurs between groups 1a and 2a. Add electrons must go from p orbitals, not s orbitals. Electrons further from the nucleus and feels repulsions in the s electrons. That's good stuff. Second occurs between groups 4a and 5a. Group 5a has no empty orbitals, and the extra electron must go into an occupied orbital, which is why you see that change. Okay, so I'm going to stop there. I believe that's the end of 7.5. And thank you for paying attention.